Welcome to another STM32 programming tutorial, and in this video we will cover digital to analog converter DAC peripheral of the STM32 microcontroller. Using this peripheral, we will generate an analog signal from the digital one. But before starting, traditionally, I want to present embedded programming and robotics courses on my website. And today I want to introduce the following course. If I have a chance to recommend one course to younger self, it will be this one. In this STM32 based attitude estimation course, first I cover essential peripherals such as SPI, UART, timer, DMA to interface with the IMU sensor. And then in the second part of the course, I cover Euler angles, quaternions, complementary filter, and more advanced data fusion algorithms such as extended command filter for precise attitude estimation. So whether you are an engineer or hobbyist, this course will give you skills to take your projects to the next level. So you can find the link in the description below, or you can press the link which appears on the top right corner of the video. So let's go back to our main topic, the DAC peripheral. So as I said before, digital to analog converter DAC is necessary to generate analog signal from the digital data. So it is opposite to ADC peripheral. So here I listed some main characteristics of this peripheral. So first we have the resolution. So in STM32 microcontrollers, it could be 8-bit or 12-bit resolution. So similar to ADC, higher resolution you have, finer analog signal you can generate. And also sometimes you have dual channel mode. So instead of having just one single channel, you can generate two analog signals. Another cool feature is to trigger the DAC peripheral using the timer. So this way we can stream the digital signal to the analog to have a dynamic signal. Next, let me show the fundamental equation in the DAC, which shows the relation between the digital value we set and the analog output. So here D is something we can control, we can set, and based on D we get the analog output in the DAC. So for example, if we use a 12-bit resolution, the D value will vary between 0 and 4095, and N is the resolution. So in our case, it is equal to 12. And here I have a very simple equation. So if we set D to 2048, we obtain the following value, following voltage level, 1.65 volts. So by varying D between 0 and 4095, we get analog signal which vary between 0 and the reference voltage, which is 3.3 volts. So this is the very short introduction of the DAC. Next, we will move to the configuration of the DAC peripheral. To configure the DAC peripheral, I use, of course, the CubeMix graphical tool. So within the analog peripherals, we just need to choose DAC, and here we need to connect the output of the DAC to the external pin. So here we also have a feature of connecting the DAC output to the ADC of the microcontroller. But right now, of course, we don't need this feature, so we just connect to the external pin. So in my case, I'm connecting both of the outputs to the external pin. And then if you look at this graphical illustration of the of the microcontroller, I can see that PA4 is the output 1, out 1, and PA5 is out 2 of the microcontroller. Then we open parameter settings and we have the following default configuration. Right now we don't need to change anything because I want to show the basic configuration of the DAC. Okay, so the next thing you just need to generate the code by pressing this button, or you can just save the file. So after the configuration, we have this function to initialize DAC, and within and to start the ADC, we just call the following function HAL DAC start, and where we need to first define the handler of the DAC, which is just over there. Then the second argument is the channel. So right now I'm using channel 2 because to this channel I have a LED connected on my board, so I can test the DAC. So you can write 1 or 2, doesn't matter. Then within while loop, I can set the value of the DAC. So for that, I have the following function, HAL DAC set value. So here we have the again DAC handler where I'm using channel 2, channel 1, doesn't matter. Then we have the resolution, so I'm using 12-bit resolution, and the final is the DAC value. So I am setting the maximum value. Then I set 2 seconds, then I set 0, I wait 2 seconds, and I repeat it. I keep doing this operation within the while loop. So next, of course, we need to debug how, just to see, just to show how things work there. So I'm going to open the debug perspective. So right now I'm in the debug perspective. So I resume the code, and as I said, the channel 2 is connected to the LED on my microcontroller. So maybe you can see it on my board. Hopefully you can see this green LED just over there. So it is blinking by 2-second delay. So which is the logic that we defined within the while loop. So everything is working well. So at this point, we know how to set some analog value, some voltage level using the DAC, and it could be useful in some applications. But in most of the cases, we want to stream some audio data to the DAC. And the classical, I think, example is audio data. So imagine that you have some buffer holding the audio data, and you want to stream that data to the DAC with precise timing to generate this audio signal. So next thing, we are going to implement this approach. And for that purpose, we need to again go back to the configuration of the DAC. So the first thing here, we need to enable the trigger. So to achieve the precise time, we need to use the timer. So I will use timer 4 to trigger the DAC, and pay attention that I'm using output 2, but in exactly the same way you can use output 1. So I'm using timer 4. So I'll go to the timer 4, and here I need to enable the timer by clicking this box. So I have an internal clock connected to the timer, and then if I open the clock configuration, you can see that the clock frequency is 80 megahertz, and here I set 79 to achieve 1 megahertz frequency on my timer. Then I have another parameter, counter period, and I set it to 999. So the update event will happen at 1 kilohertz. And if you want to know more about these parameters, you can refer to some of my videos on my channel or to the STM32 programming course on my website. So here I set this to achieve 1 kilohertz, and then I have this trigger event selection, and among these options I need to choose update event. So update event will happen at 1 kilohertz, meaning that every 1 millisecond we will update the DAC value. Next we go back to our DAC, we go to DMA settings, and to stream the data, of course we need to use the DMA, and here we have one single option, DAC channel 2. Then we need to use circular mode just over here, because once we enable the DMA, it will keep streaming the audio buffer to the DAC. Okay, this is how it's gonna work. And here we have the data width, half word. We'll increment the memory. This is a default configuration. You don't need to change anything. So that's it. That's how we configure the DAC for buffer streaming. So we go back to our project. So don't forget to also to generate the code by pressing this button, or just save the file. Once the code generation is over, first I want to create some buffer, and instead of just filling it with some random values, I decided to create a pure tone at 5 Hz. So we have DAC frequency at 1 kilohertz, we have a pure tone 5 Hz, and we need a buffer which contains one period of the signal. So to get the buffer length, I take the frequency, I divide by the signal frequency I want to generate. Then I have a sine function to generate the sinusoidal signal, and I have this offset to have always positive values. So I use this for loop. So okay, we fill it, then we call this HAL DAC start DMA, and as I said, if once we start it will keep streaming the buffer. So here we have DAC 1, we're streaming to channel 2, we have this buffer pointer, we have the data length, and we have 12-bit resolution. And also, of course, we should not forget to start the timer, so it will trigger the DAC, or to be specific DMA. So every 1 second, every 1 millisecond, the DMA will update the DAC value using this array we created. So that way we can create some dynamic signal, and you can easily change the frequency. So here I have 1 kilohertz, or we can make 16 kilohertz, 32 kilohertz, and instead of just a pure tone, you can fill this buffer. You can fill this buffer with the real data. So that's it. Next, we are going to debug to see how it works. So I'm in debugger perspective. So I resume the code, and next I'm going to show the result. So here it is. So as you see, this green LED is blinking at 5 Hz. So everything is working as we expected. So the final note is that the project source code is available on a GitHub steps organization, and you can get access to it and to all other materials I've worked so far by becoming a patron, a member of my community. If you like the content, don't forget to smash the subscribe and the like button. It will help me to reach a new audience. So that's it for today. Thanks a lot, and see you soon.